Ladies and gentlemen, this presentation of 66 slides concerns the subject of climate change, greenhouse effect, global warming and El Niño, based on historical trends of rainfall, river flows and atmospheric temperature profiles. By investigating the data, we dedicate this presentation to all people who have collected climatological data over the last 3 centuries, the oldest for rainfall from 1707, and some are missing in periods of war. Meteorological forecasts are extremely helpful, but what are the regional trends of rainfall that cause floods and drought? The slide presentation is based on a booklet of 32 pages with an attached CD-ROM containing plots, original data and additional information. Readers possessing a personal computer can open all files and continue the research for their own region with the data provided. The content of this presentation is about global water withdrawal, rainfall, river flow and temperature trends, climate forcings and effect on water resources. Is our need for water increasing? An increase by 80% per century is predicted by the literature. Can the total rainfall on the continents provide enough water for this increase of demand? Our research shows an increase of 1.21% per century. Published calculations give a global increase of 1.7% per century, split up in plus 8.2% per century for the continents and minus 0.1% per century for the oceans. But where on the continents will it rain more in the future and where will it rain less? 4 examples are presented here out of the 186 stations studied. Since 1890, the annual rainfall in Moscow is increasing by almost 18% per century. Since the pattern of alternating extremes remains the same, the highest extremes are increasing too. For Tokyo, Japan, the rainfall remains almost constant since 1877. A slight decrease of 4% per century might not be significant. This is different for Beirut in Lebanon. A rainfall decrease of 32% per century is observable since 1889, while annual large irregularities of high and low rainfall persist. This means that the risk for drought periods increases. This becomes also clear when plotting the same data of Beirut for the months of January to December. For some years, and outside the dry season between June and August, dry periods have been observed as well, in a number of years in the other months. The rainfall decrease of Santiago, Chile, is about 18% per century. Similar as for Beirut, where low and high rainfall years alternate, the risk for larger drought periods increases, and this region has already a low rainfall. Large differences exist for the rainfall trends for the 186 stations of all continents. The plotted correlation line gives some general tendencies, but has a low significance. The most striking conclusion is that the continental rainfall trends are equal from before and after the period when the greenhouse effect started in the late 19th century. An explanation could not be found from our data. As already mentioned for Beirut and Santiago, Chile, the question is posed whether climate extremes seem to increase in frequency and in impact. Flooding in Bangladesh and how to survive. From 1950 to now, the reinsurance company Munich Re calculated that the losses from environmental disasters increased in the last 50 years from 5 to 60 billion US dollars per year, of which only 1/3 was covered by insurance. What can we learn from changing river flows? Are the trends the same as for rainfall? River flow sampling in Argentina. The river flow trend of the Mississippi, USA, makes it clear that as from 1927, the river runoff increased by 60% per century. Regular flooding will intensify. There is no doubt about that. For the Senegal River, the problem is reversed. The river flow trend shows a disastrous pattern towards increasing drought. A great number of rivers have increased or decreased runoffs. Thus, indeed, many river flow trends follow those of the rainfall trends. For all stations together, the average trend is negative by 7% per century, in contrast to an average increase in rainfall of 1.21% per century. The withdrawal of water and technical regulations make up the difference. The next section concerns the regional and global atmospheric temperature changes. We don't lack messages in the press on global warming, which sometimes are contradictory and alarming. Our questions are, is global warming the same everywhere? And does the complete atmosphere participate? How did the global temperature behave since the Middle Ages? For the last 1,000 years, until 1900, surface temperature decreased by 0.2 degrees Celsius. This result was deduced from growth rings of trees. By 1900, the global warming started due to the greenhouse effect. Our data on atmospheric temperatures cover the last 50 years for altitudes from 1,000 to 10 hectopascal, which is from 0 to about 27 kilometers high. As an example, we have taken Bombay in India. Although difficult to see, the slide presents the monthly temperatures from January 1948 to July 2001 for each selected pressure. In this slide are plotted those temperatures at 1,000 to 200 hectopascal, which is 0 to 10 kilometers high. Of the linear regression line, function y is ax plus b, the index a represents the temperature trend at that pressure level. For higher in the atmosphere, 150 to 10 hectopascal, which stands for 15 to 27 kilometers high, the same pattern is found with an excessive temperature increase at 10 hectopascal, or at a height of 27 kilometers, the upper line. The two plots require some additional explanation. Plot A is the temperature profile in Bombay in July 2001. Plot B gives the measured and corrected temperature profile trends. The left graph. In Bombay, it is warm in July at the Earth's surface, where the temperature cools down to minus 80 degrees Celsius at 70 hectopascal. Above this level, it is less cool until minus 40 degrees Celsius at 10 hectopascal. The right graph, blue line, these are the measured temperature trends in degrees Celsius per century. Low at the Earth's surface, highest at 100 hectopascal and negative at 50 hectopascal. The red line represents the corrected temperature trends linked to the heat required for warming or cooling. The term corrected temperature trend is explained in the next slide. An increase of 10 degrees Celsius per century at 10 hectopascal requires the same heat as an increase of 0.1 degrees Celsius per century at 1000 hectopascal, the Earth's surface. Thus, the corrected temperature trend at 10 hectopascal is 0.1 degrees Celsius per century. In the following two slides, we will see how different the warming occurs in the complete atmosphere. This plot of trends at 75 continental stations represents the measured temperature trends in degrees Celsius per century, where the brown line concerns the trend at the pressure level of 10 hectopascal at a height of 27 kilometers. The highest trends are towards the poles, with for Antarctica an exceptional warming of plus 35 degrees Celsius per century. For the corrected temperature trends, representing real warming and cooling, the temperature trends at 10 hectopascal are close to the x-axis. Interesting are the regional differences. We will now calculate the global continental average of the corrected temperature trends for the complete atmospheric profile. On the left graph are the corrected temperature trends at different pressure levels, 1000 to 10 hectopascal. The right graph shows the same trends, but plotted against height in kilometers. Note the cooling in the stratosphere. This means that the difference between the temperatures in the troposphere and stratosphere increase with about 1.4 degrees Celsius per century, thus affecting the atmospheric stability negatively. Continental warming of the complete atmosphere is plus 0.34 degrees Celsius per century, requiring 1.1 watt per square meter per century. This is 0.3% of the approximate insolation received on Earth. This is not very much, really, only 3% per millennium. How can the warming below and above the stratosphere at 10 to 24 kilometers and the cooling of the stratosphere be explained? A kind of double greenhouse effect is the cause. When sunlight containing infrared light enters the highest atmosphere, it meets greenhouse gases, which will absorb radiation. So the stratosphere and the troposphere are exempt from part of the solar insolation. Infrared radiation from the Earth's surface is increasingly absorbed by the greenhouse gases in the troposphere. The result is that the higher atmosphere, in particular the stratosphere, is exempt from this radiation. The cooling trends of the stratosphere can be explained this way. What is climate forcing? It concerns processes that are responsible for climate changes. We mentioned already the double greenhouse effect due to increased CO2 in the atmosphere. We will now discuss the greenhouse-related ocean circulation, the glacial and interglacial trends, known as the Milankovitch effect, and the El Niño-induced rainfall and river flow changes. In a period of about 1,000 years, the deep ocean is refreshed with surface water descending in the North Atlantic during wintertime. Warm Gulf Stream water penetrates far into the North Atlantic and Arctic Sea and is in the wintertime descending to form the Atlantic deep water and the Arctic bottom water. These water masses slowly migrate to the southern Atlantic, Indian and Pacific Oceans. The cartoon of the Great Conveyor Belt appears in many publications. It involves the ocean circulation between the deep and surface ocean water. The theory is that when the Gulf Stream becomes warmer and receives more fresh water from melting Greenland ice, its density becomes less. The result is that in the winter, less cooled water will descend to deeper layers. Thus, the Great Conveyor Belt slows down. The result is that the climate in Europe will change from maritime to continental, a situation already experienced during the small ice ages from 1400 to 1800. Is the Gulf Stream already warming up? Here are given the surface seawater temperatures for 3 stations. The highest warming is in the center of the northern branch of the Gulf Stream, near the Faroe Islands. The warming trends are equally positive at more remote stations. It proves that the process of warming of the Gulf Stream exists. The next section concerns the interglacial and glacial cycles. During glacial periods, the sun radiation is 10% less than during interglacial periods. Our present interglacial period has lasted already for more than 10,000 years. The question is, are we approaching a new glacial period? The glacial and interglacial periods are caused by 3 astronomical processes. The first are cyclic changes in the precession of the Earth axis. The second are changes in the obliquity of the Earth axis. And the last are cyclic changes in the eccentricity of the Earth rotation around the Sun. Model calculations of these cyclic changes indicate that the regularity of the last 1 million years will change. The chance for a new glacial period is still far away, since the cooling, which started 10,000 years ago, will not proceed but will change in the next 10,000 years to a slight warming. In conclusion, there is no fear for a new glacial period, but the greenhouse warming of the North Atlantic may change Europe's climate from maritime to more continental. Severe winters, during the small ice ages in the year 1634, for example, were painted by famous Dutch painters. Are climate changes of shorter periods influenced by the greenhouse effect too, such by El Niño, for example? In 1997, there was a strong El Niño. The seawater temperatures near Ecuador and Peru were far above average. See the plate above. The records of the El Niño Southern Oscillation, known as ENSO, is based on the monthly surface atmospheric pressure differences between Darwin in North Australia and Tahiti in the Pacific Ocean. Over a period of 100 years, no coincidence can be observed between the years of extreme rainfall and river flow and the years of El Niño or La Niña. This was observed at 36 rainfall stations and 5 rivers of South America. The only exception is Peru and Ecuador. Water resources are linked to the balance of water in river basins. They depend on rainfall, evaporation, runoff, use, and groundwater. Real evaporation can be found in maps of atlases. Potential evaporation should be calculated. The World Meteorological Organization, WMO, provides guidelines for the calculation of the potential evaporation based on a number of case studies, of which one is available on the CD-ROM. From this case study, the potential monthly evaporation of a number of stations is plotted here. For the same stations, the annual rainfall, here in red, is usually lower than the potential evaporation, indicated in green, except for Tokyo. Here lays a large task ahead to avoid overexploitation of the water resources of a river basin. The greenhouse effect is caused by increasing CO2 levels in the atmosphere. Does increasing CO2 affect seriously the acidity of sea and freshwaters? The oceans have a buffer pH of 8.1. When all fossil fuel reserves will be burned up, the pH will not drop below 7, which is neutral. Freshwater systems are not buffered and have already large ranges of pH due to substances other than CO2. No general prediction can be given. We already mentioned the vertical gradient trend of 1.4 degrees Celsius per century. This increases the density instability of the atmosphere, enhancing the development of thunderstorms, hurricanes, and depressions. This, in particular, in regions that are already sensitive to hurricanes, here indicated in green. Our general conclusions are that, first of all, water resources will suffer in regions with negative rainfall trends. Second, that the number of regions exposed to extreme flooding and drought will increase. And lastly, that the global average warming is composed of a very diverse regional warming and cooling in the total atmosphere. See for detailed information the booklet and the attached CD-ROM, in which are presented 186 rainfall graphs, 180 river flow graphs, and 75 temperature trends from all over the world. The booklet is entitled Rainfall, River Flow and Temperature Profile Trends, Consequences for Water Resources. It is available at this Third World Water Forum. The directories of the CD-ROM reflect those of the chapters of the booklet. Added are the original data bank records and directions for your further research. The booklet and CD-ROM are sponsored by the Heineken Company with as objective to stimulate regional research on climate changes and finding solutions to the regional water challenge. This presentation is in honor of Dr. Alfred Heineken, founder of the academic prizes awarded by the Royal Netherlands Academy of Arts and Sciences.